Okay, good morning. This is Jose Manuel Campos Salazar, and together with my colleagues Felipe Santander and Sebastián Larraín, we're pleased to present our work titled Dynamic Modeling and Control Analysis for continuous disk filters in Pulp-Mill operations. This presentation is part of 2025 International Chemical Recovery Conference here in Toronto. The focus of our research is on developing a dynamic model of CD filters, key solid liquid separation unit used in pulp mills, and try to apply some control strategies to improve their efficiency and stability. Our contributions integrate nonlinear modeling, state space formulations, and control designs, with a particular emphasis on comparing both strategy and a centralized proportional integral control against to a centralized model predictive control strategies under some dynamical scenarios. Here is the roadmap of today's presentations. Basically, we begin with introduction, where I give some context about Arauco and the role of these filters in Pulp-Mill operations. Next, the process description will outline how the CD filters works, including some key variables and physical principles. Then, in system modeling, I will present the nonlinear dynamic model, the assumptions made, and the state variables considered. After that, we will review CD filters efficiency, which is quantified through solid retentions. Moving on, I will explain the control system description, where two basic strategies are analysis, and a decentralized PA, proportional integral control, and a centralized model predictive control. This will lead us into the simulation results, comparing the performance of both controllers and highlight some key findings. Finally, we will end with some conclusion which summarize the main contribution of these works. So let's get started. Okay, Arauco is a vertically integrated global leader in sustainable forestry and forest products. Arauco lives here in Chile, basically. Now, its mission is to transform renewable forest sources into solutions for everyday life, but at the same time, maintaining a strong commitment to environmental stewardship, innovation, and community development. Basically, this company has run 7 mills in Chile and Argentina, producing approximately 4.5 million tons annually, ranging from the market kraft to dissolving and fluff pulp. Now, these mills supply a global paper, dissolving, and special industries. But beyond the pulp, Arauco is also one of the major producers of wood panels, around to 8 million meter cubic per year. And also, this company is a significant generator of renewable energy, around to 1,078 megawatts per year. So this data reinforcing its role as both industrial and sustainable benchmark. As you can see here in this slide, in 2024, this company operated globally across the Americas, Europe, and even in Africa, with approximately around to 1 million hectares of forest assets, and around to 20,000 employees at the world. Now, the company produced, as I mentioned, almost to 8 million per meter cubic of wood and panels, and 4.6 million tons of pulp, and generated approximately 1,078 megawatts of clean energy. But also, this company invests around to 40 million in research and development, reinforcing its leadership, basically in sustainability and competitiveness. Now, let's talk about the CD filters. CD filters are a key solid liquid separation unit used in pulp mills, especially for pulp washing and quite deeper clarifications. They consist of multiple porous discs rotating through a slurry under vacuum, forming and discharging cakes. the dynamics of the cake thickness and dryness are directly influenced by rotational speed, vacuum level, and slurry concentrations. These variables strongly determine throughput, filtrate clarity, and overall chemical recovery efficiency. But it is important to recognize that this machine remains unrepresented under our point of view in modeling and control research. Most existing work are empirical or steady state, which fail, as you may know, to capture the nonlinear coupling between cake growth, for instance, filter flow, and mechanical dynamics. Even more, in practice, Mill often rely on decentralized PI loops or even manual operator intervention, which, as you may know, are insufficient to handle multi-variables interaction and process constraints. Now, let's move on to the process description of this machine. Basically, here we will look at how the raw white liquid vacuum and cake formation interact inside of this machine and how these variables define the overall dynamics. This slide introduces the process description of these CD filters, using basically in this kind of mill. This filter, as I mentioned before, consists of a movable porous disc rotating through a slurry under vacuum, allowing the formation and removal of the fiber cake on their surfaces. As shown here, as you can see, the three main streams are involved. The raw white liquid, which is related to these variables. Then I got another output stream, which represent as a filtered white liquid, labeled as a QF and CS, and a third stream, which represents the mud flow, which removes the cakes, represented by this concentration here and this flow. Now, it is important that for modeling purposes, instead of use the full 15-disc industrial unit, which you can find in the market, this system was reduced to just a one single equivalent disk, which captures the averaged dynamic, at the same time simplifying the analysis. Now, the system dynamic are described basically by 5 key coupling variables, and that was our method in order to describe these systems. The angular velocity, vacuum pressure, slurry concentration, cake thickness, and the filtrate flow or filtered white liquid. Now, these variables interact through pressure differential, as you can see here, and also appears some resistance coming from, for instance, RC, which is the filtered cake layer resistance. Then we can find another resistance we denote as RAM, which represents the main resistance, and the total resistance, which is the compromise of both resistance as a summation. Now let's move on the system modeling. At this stage, the focus shifts from the describing physical process to development mathematical representation of this machine. Now, as you may know, CD filters exhibit inherently nonlinear dynamic due to the tight coupling between mechanical rotation, vacuum drying filtration, solid transport, and cake formation. To mathematically capture this interaction, we just built a multivariable model based on 5 key state variables: shaft angular speed, vacuum pressure, slurry concentration in the bed, cake thickness on the disc surface, and finally the filter flow rate. Now, in order to ensure some tractability, simplifying assumptions are made. For instance, incompressible cake, a single disc equivalent capture, as I mentioned before, all the averaged behavior of the system, continuously solid removal, constant filtration area, and omission of backlog control. Now let me move into each dynamical equation which form this system. Rotational speed dynamic. This slide presents a rotational speed dynamic of the CD filter governed by a torque. Basically, this is a torque balance, basically, in order to get this equation. The modular torque here and the resistance torque here. Especially this torque coming from hydrodynamic drags, okay, friction, and mechanical losses, as you can see here. So the first equation here representing this dynamic is presented as is that I'm showing now here, where J is the total inertial as you can guess, right? Now, also we could find some linear relation in order to represent the resistive torque, which is modeled is modeled using this equation that I'm now showing here, where KD is a damping coefficient, constant damping coefficient, and KC is the K resistant coefficient. Now it's interesting this because, for instance, the KD represent, as I mentioned, viscous damping from the slurry flow, and KC accounting for cake resistance due to the scraping while the system is working on. Finally, if I make a substitution of this equation into here, we finally get our final dynamic equation representing this dynamic. Now, it's important to know that physically this relation shows the higher viscosity, thicker cakes, and faster rotations increase somehow or resistive torque, directly influence the cake formation and, of course, the removal. Now, let me go to the next dynamical equation, which represents the vacuum pressure dynamics. This slide explains the role of vacuum pressure PV in the main driving force filtration, which is governed by a gas balance receiver. Receiver is another equipment which is not shown in this process description diagram, but is putting far away from the output of the stream output of the system. RG is the gas constant, T is the absolute temperature, and of course, BG is the receiver volume. Now, it's important to recognize that inflow, represented by QR in, rises with cake permeability. At the same time, we're gaining the vacuum, while outflow, QR out, depend on valve performance strengthening it. Now, we just find analyzing this equation that once maximum permeability is reached, further vacuum depending just dimension returning liquid extraction. Now let me go to the next dynamic equation, which represents the slurry solid concentration dynamics. In this part, basically we focus on the evolution of the slurry bed solid concentration, denoted as CR, which is governed by a mass balance over the bed volume. So this is a mass balance, basically. Mathematically, we describe it as a net inflow of solid through the roadway liquid feed, which is represented by this first member of this equation here. Minus, of course, the solid removes with the overflow, which is represented by this part of this equation here. Now, it's important to know that the outflow term captures both filtrate flow and mold removal, making this concentration highly sensitive to upstream feed composition, filter efficiency, and discharge performance. So disturbances such as, for instance, clarifier carryover can propagate through this pathway, making this concentration as a key control barrier for CD filter stability and optimization workspace. Now let me go to this dynamic equation, which represents the cake dynamics. Basically, here we focus on the cake thickness dynamic of this machine. Now, the state variable here, HT, represents the cake thickness and involves from the balance of the position and removal, as you can see here in this equation. Now, this governing equation shows, as you can see here, that the position is proportional to the slurry solid concentrations. And also the filter flow QF in both terms, while removal is proportional to the rotational speed, as you can see here, and the existing cake thickness. Also, important thing here is that operationally, this speed is tuned to maintain charged cake thickness, ensuring a proper deweighting without excessive buildup of the cake. I mean, in terms of the cake. Now, let me go to the final dynamic equation, which represents the filtered white liquid flow dynamics. This slide, as I mentioned before, represent this dynamic, and the flow is governed by basically Darcy law, where the pressure differential across the cake and medium drives liquid transport is the main driving force for this dynamics. Mathematically, this dynamic is represented by this equation. It is important that the cake resistance RC, which I mentioned before, depends on the thickness, medium resistance REM, and at the same time, the REM is more or less constant. So standing cake discharge lowers RC and rises QF, while increases vacuum, strengthens the delta P, and boosts the flow. So this last equation coops fluid transfer with cake growth, coupling all nonlinear dynamical equations. Having said that, now let me show the steady state model. Why? Because we just used a classical control design, which is more easy for us to get some linear model. So the step before that is to get the steady state operation point. Now, this slide shows the steady state model of this machine. To build this, we just tested all the time derivative from the nonlinear dynamic equation to zero, which allows to basically derive all the algebraic constraints for instance, turbulence, vacuum equilibrium, solid continuity, cake build-up, and filtrate flow. Once we solve this algebraic system equation, we can get our desired operational point of the system, which are represented in this equation, in these equations here. So, having this, we are able to get our finally linear equation using a first-order Taylor expansion, yielding a finally a continuous time state space model, linear model, and deviation value. So with this equation, we can just make the synthesis for controls. But before that, let me show our ratio, what we found as a CD filter efficiency. Here, this slide explains how we quantify CD filter efficiency, basically. Efficiency measures the fraction of solid retained compared to solid entering into the system, as shown in this equation here. Essentially, it tells us how well the filter is separating solid from the slab. Of course, in order to get this ratio, we assume, for instance, a perfect mixed batch, meaning that all the solid incoming suspicion are equally likely to contribute to K formation, basically, the no bypasses. Now, the evolutions of the efficiency reflects that the combining effects of vacuum level, rotational speed, and slurry concentration are working together. So, deviation in this efficiency signal fault such as, for instance, media fouling, why not, K compaction, or inadequate vacuum. Also making it as a key indicator in our point of view for a real-time monitoring, diagnostic, and predictive control for CD field task on the future, for instance. But you should know that this equation we just implement in our mirror DCS system. Now this equation is in a testing loop, basically is in a testing in order to get finally some result, in order to validate this and just use it for control, not for monitoring only as in this time. Okay. Up to this point, we have reviewed the nonlinear dynamic of this machine, Now, let me introduce the control strategy implement to achieve high-performance closed-loop regulations. Basically, this slide presents the first control strategy implemented into the CD filter, but we just used or designed two control strategies, one PI and another MPC. The first loop, as you can see, regulate the shaft. I mean, and this PI controller, we just configure 3 loops. Loop 1 regulate the omega via motor torque directly linked to the inflow, the rock or liquid flow. Then the loop 2 regulate the slurry concentrations by basically adjusting the CAN. And the third loop is in a cascade structure, which basically for filtrate flow, as you can see here, with an outer loop setting vacuum here, and an inner loop regulating the PV via QAR, as you can see here. The MPC is just a block where we finally control the QF or output filtered white liquid and the concentration. In this block wasn't necessary to develop a inner loop in order to regulate the omega or the rotation speed. It was just necessary to regulate directly these variables. The other ones act as a measure output, basically, here, as you can see here. So now let me move into the simulation results. Basically, in this figure, present the closed loop simulation result for a slurry concentration under both strategy of control. On the left side, we see the transient tracking response, basically the PI control exhibiting a fast initial action, but with some excessive oscillation at the first time. A large overshoot of around 52 with some integral square error approximately to 2 times 10 power 4, confirming a poor damping if you put it that way. In contrast, the MPC achieves smoother dynamic with reduces overshoot approximately 36% and a much lower ICA of 1.52 basically. So MPC yielded a smaller transit, reduced an overshoot and a lower ICA. But also we can see an 80% lower error variance, as you can see in the right side, in the picture put it on the right side of this slide, confirming so a superior precision and disturbance rejections. In this slide, we compare the regulation of filtered white liquid flow, QF, under both controllers. The PI loop delivers acceptable tracking, but present approximately 2% overshoot, a 30 time of 4 times per second, and an ISA with some values are really low. By contrast, basically MPC completely eliminate overshoot, as you can see here, reducing the settle time to 3 seconds and maintain a comparable ICA. So MPC constantly outperforms from PI, especially in coupled dynamics and error variance, believing its effectiveness in multivariable filter control and another stuff like the rate shown before. Also, here we have a final simulation analysis of the CD filter efficiency. A 3D efficiency surface shows that this efficiency rises non-linearly with the inflow rate and feed concentration, which is represented by this equation here. So highlighting the need for coordinated multivariable control to maximize solid retention, we just found that. In order to end, let me tell you what were our conclusions. This work basically presents a nonlinear dynamic model of this CD filter, simplifying to a single disk equivalent for tractable control synthesis. The model captured the couplings between rotation, vacuum, slurry concentration, and cane growth and filtrate flow. Competitive simulation showed that MPC outperforms PI by reducing ICA, overshoot, and settle time, especially in coupled variables such as a vacuum and slurry concentrations. Error analysis confirmed MPC's higher precision and lower variances. The efficiency surface highlighted the need to coordinate control and or feed flow concentration. Now, overall, MPC proved superior traceability, robustness, and efficiency, making it a strong candidate for industrial CD filter optimization. Thank you so much for attending this presentation, and question if you have some. Thank you.